the last lecture, we described marine towed streamer seismics and broadband seismics. We will now describe ocean bottom seismics, that is, an acquisition where sensors are located at the sea floor. The towed streamer experiment records P waves, but no S waves are directly recorded, although the wave path below the seafloor may include some S wave paths. The S waves are not directly recorded because the receivers are in seawater, and water, like all non-viscous fluids, supports only P waves, not S waves. In a marine ocean bottom seismic, or OBS experiment, which is also known simply as a marine 4C experiment, the receivers are located at the sea floor. We directly record S wave arrivals along with P wave arrivals. Every receiver station is a 4-component or 4C sensing system. 3 components of the particle velocity field are recorded from a 3-component geophone, and the pressure field is recorded from a hydrophone. Here is a mathematic description of 4C recording. We have a measurement of pressure variation in the water using hydrophones. And we have 3 components of the particle velocity, which measure the seafloor motion using geophones, which are coupled to the seafloor. Here is one of the first 4C sensors. It was developed in the late 1980s. It housed a hydrophone to measure pressure and 3-component geophones to measure the particle velocity vector. This sensor consists of a 30-centimeter long, 6-centimeter diameter spike, which is used to plant it into the sea bottom by a remotely operated vehicle, or ROV, to achieve good coupling. Above the spike is a geophone housing, approximately 40 centimeters long. On the top left is the hydrophone housing. Those days, the ROV crew used approximately 1/2 hour to plant each 4C sensor. Our objective here is to provide a description of ocean bottom seismic experiments and of ocean bottom seismic data, including the benefits of this acquisition for illuminating the subsurface. The use of ocean bottom seismic experiments and of ocean bottom seismic data for permanently monitoring reservoirs is one such benefit that we will describe. We will also describe the major challenges of ocean bottom seismic acquisition. Some of the key learning outcomes will be to familiarize yourself with the benefits of recording S-wave arrivals in addition to P-wave arrivals. Familiarize yourself with the problem of coupling geophones to the seafloor. Familiarize yourself with the notion of vector fidelity. Familiarize yourself with the concept of reservoir monitoring, especially permanent receiver monitoring. Let's start with OBS acquisition geometries. Here is one OBS acquisition geometry. It consists of 2 vessels, one recording vessel and one shooting vessel, which tows one or more energy sources. The black straight lines are streamers of receivers. When the shooting is completed and the cables are redeployed in a nearby location, the shooting campaign continues. Note that the shooting is stopped during the redeployment of receivers to the new locations. Note also that the recording of all these components are possible in water, therefore in the towed streamer seismic or TWS experiments. However, the TWS particle velocity data will not include S-wave arrivals. That is the difference between OBS and TWS. OBS surveys are not limited to 2-vessel operations. To speed up the data acquisition process and thus reduce cost, 3-vessel operations are also common. While the source boat is traversing the survey area and the second vessel is recording, the third vessel is involved in retrieving and moving sensor cables and setting up the next receiver lines ahead of the source vessel. This three-vessel configuration allows the source boat to run a nearly continuous operation. An alternative ocean bottom acquisition is the node system. This figure contrasts ocean bottom experiments using either cables with nodes. In ocean bottom node type systems, sensors housed in units which are inserted into the seafloor by remotely operated vehicles. Recording must take place locally, inside the sensor unit. Nodes generally have better coupling than cables. In addition, nodes are suited for the areas with obstacles such as pipelines, anchor chains, and wellheads. One of the major requirements in 4C OBS experiments is that geophones be well coupled to the seafloor in order to record both high-quality P waves and S waves. Because shear waves do not travel through water, the geophones must be in direct contact with the seabed to capture the motion of the seabed and not the change of pressure in seawater. Sensors must be coupled to the seafloor to capture motion of the seafloor with time. The process of ensuring direct contact between the geophones and the seabed or any other solid material is called coupling. The 4C OBS experiment requires precise coupling of geophones with the seabed. In ocean bottom cable acquisition, weights are added to the cables so that sensors attached to cables capture the seafloor motion. This solution is generally effective for soft sea floors and less so for hard sea floors, like in places where basement rocks are exposed on the seafloor. The reflection coefficient at normal incidence of the seafloor can be as much as positive 0.8 in this case. Offshore eastern Canada, where the hard bottom problem typified the coupling challenge with OBS acquisition with cables and even with nodes. Nodes generally have better coupling than cables because the remotely operated vehicles, or ROVs, can be used to ensure a good coupling of sensors with the seafloor. However, the deployment of nodes is still very expensive. About 4 nodes can be deployed per hour in 2016 with ROVs. A small survey of 5,000 node locations can last 50 days. Another important requirement of OBS surveys is the so-called vector fidelity. Vector fidelity can be defined as that property of a 3-component geophone sensor system, wherein a given particle motion impulse applied parallel to one of the sensor components registers only on that component, and wherein the same impulse applied parallel to the other components gives the same response, so that the various components can be combined according to the rules of vector algebra. 3-component geophone recordings obeying vector fidelity thus are in agreement with the true Earth motion generated by seismic waves at the seafloor. At a minimum, vector fidelity can be constituted as follows. 1. There is no substantial leakage of energy from one geophone component to another orthogonal component. 2. There is no significant azimuthal bias in the recording of horizontal component geophone data. 3. There is no prominent noise events that lack a geophysical origin, for example, mechanical resonance. And 4. Bandwidth, transfer functions, and coupling of all 3 components to the seafloor are substantially identical. Note that vector fidelity depends upon the type of sensors, the housing, the coupling with the seafloor, and the method of sensor deployment. Vector fidelity of the sensor system is required for all current processing methods based on the elastic wave theory. As described here, there are now two major ways of collecting OBS data: the streamer or cable acquisition and the node acquisition. A number of OBS developments in recent years involve node acquisition. It has taken a while for the ocean bottom node technology to take hold. Until 2008, a maximum of 2 commercial ocean bottom node surveys per year were acquired worldwide. Since 2008, this number has jumped to more than 10 surveys per year, and demand from 2013 onward is increasing. The need for azimuthal coverage in the imaging of complex reservoirs and the progressive adoption of permanent seismic installations at the seafloor by the industry are the key reasons for increasing ocean bottom node surveys. The remaining challenges in node acquisition are the sparse distribution of receivers in both the X and Y directions, and the significant cost of surveys generally associated with the use of ROVs. Another major area of OBS development in recent years is the use of fiber optic cables. The key attraction of fiber optics for subsea use is that no electricity is needed at the sensor in this system, removing one power demand and potential hazard. In addition, they can operate in ultra-deep waters. Continuous recording can be done in a buoy at the surface to eliminate the requirement of a recording vessel, just as with nodes. Here is a brief comparison of TWS and OBS experiments. In TWS, sources, for example air guns, are in the water. Only P waves are generated. In OBS, it's the same. Sources, for example air guns, are in the water, and only P waves are generated. In TWS, receivers are in the water. Only P wave arrivals are recorded, although the wave path below the seafloor may include some S wave paths. In OBS, pressure receivers, or hydrophones, are located at the seafloor, in the water, and record only P wave arrivals. Velocity receivers, or geophones, are coupled to the seafloor and record P and S wave arrivals. In TWS, major pros of TWS are that 1. It has become very cost-effective to operate through years of technological advances. 2. It provides by far the highest data quality of all the surface acquisition systems. And 3. It generally has higher receiver count than the other surface acquisition systems. In OBS, major pros of OBS are that 1. It can operate waters that are too shallow for TWS. 2. In areas with too many obstacles for navigation of towed streamers, it can also operate in. And 3. We can have very dense coverage of shot points because the shooting boat is light. It does not carry streamers. 4. The receivers can be left permanently on the seafloor, such as 4D seismics. In TWS, major cons are that currents, tides, and other forces can cause streamers to feather or drift laterally from programmed positions. 2. The sea surface harsh environment or roughness can cause sensors to break out and introduce swell noise in the data and consequently cause acquisition downtime. 3. It is very difficult to repeat TWS for reservoir monitoring. Cons of OBS are 1. The coupling of geophones to the seafloor, and 2. Maintaining vector fidelity. 3. The quality of OBS data is still well below that of TWS data. And 4. The receiver count in OBS is also generally small compared to that of TWS data. 5. OBS acquisition and processing is still quite expensive compared to TWS. Let's now talk about ocean bottom seismic data. Here is an example of real OBS shot gathers. Notice that the direct wave does not have a linear move out, as in TWS data. Although seismic events in OBS data can be cast into direct waves, primaries, ghosts, and multiples, just as in towed streamer data, their wave propagation paths are quite different, in particular those of direct waves and receiver ghosts. Our objective now is to describe these differences. Here are examples of primaries, receiver ghosts, that is, receiver side reverberations, and free surface multiples, that is, source side reverberations, in OBS seismic data. Notice that a significant number of reverberations in the water column are categorized as receiver ghosts. In the towed streamer experiment, the direct wave describes the wave propagation in the water only. It does not carry any information about the subsurface, and therefore it is generally muted from the data. The effect of receiver ghosts is also negligible in towed streamer data. It is generally treated as part of an effective source signature because the receivers are very close to the sea surface, except in the case of bad weather, in which case the receiver depth can be quite large, 10 meters or more, to avoid ocean swell. In an OBS experiment, the problem is quite different. The direct wave carries information about the structure of the seafloor, and a significant number of reverberations in the water column are categorized as receiver ghosts. An illustration of typical OBS events is shown here. When the recorded OBS wave field is a pressure field, there is a sea bottom reflection arriving at almost the same time as the direct wave. These two events are sometimes treated as one single event. In this definition of a direct wave, the effect of the sea bottom reflection can be treated as adding another virtual source to the actual source. This photo here shows an OBS direct wave with an exaggeration by putting the receiver well inside the water column. Notice that the pressure data and the normal to the seafloor component of the particle velocity data contains direct waves, since the normal vertical component of the particle velocity is continuous. We can consider the normal component of the particle velocity as recorded above the seafloor. The horizontal components of the particle velocity data do not contain direct waves because they are zero above the seafloor. See one of the previous lectures on the boundary conditions at the water-solid interface. A receiver ghost is defined as an event whose last reflection was from the sea surface. The main difference between receiver ghosts in the OBS and streamer surveys is the larger time separation of the OBS receiver ghost from primaries. The OBS receiver ghosts tend to look like multiples as the water depth increases. Summation of the hydrophone and vertical geophone component data removes receiver ghosts. This summation is described in detail in future lectures. Notice that only the pressure data and the normal component of the particle velocity data contain receiver ghosts. The horizontal components of the particle velocity data do not contain receiver ghosts because they are zero above the seafloor. See previous lectures for a more detailed discussion of the boundary conditions at the water-solid interface. Since the source in 4C acquisition is a marine source emitting P waves, any measured shear wave energy must originate from P waves being mode converted to S waves. The most energetic and useful S waves that are recorded turn out to be in most cases those which have been generated on reflection. Some of the benefits of 4C technology are from PP reflection data alone. It is sometimes difficult to differentiate some lithologies in poor saturants. Let's repeat this, and please pay close attention. From PP reflection data alone, it is sometimes difficult to differentiate some lithologies in poor saturants. Since PP and PS reflections are affected differently by variations in rock properties and pore fluids, multi-component OBS seismics have become an important tool for both exploration and reservoir evaluation because they contain both PP and PS reflections. The benefits of 4C technology can be divided into three broad categories.